to show the utility value which are, let me say, expectable for the less deformable metallic structure, which is based on hexagonal compact unit crystalline properties of the materials, even though they are not hexagonal. So, very special application, replacing nickel-based superalloy of a turbine on an aero engine, the gamma titanium aluminide, and you have yet reasons because of the nickel-based superalloys now have very good performance combined with a very reduced value of the mass density for our complex system. We discussed about this. So to summarize, my major benefits are related to the increase of oxidation temperature, drawback that is concerns on ductility at room temperature, and here you have some other, let me say, potential studies, investigated formulations, which are all based on with the just to underline to you that they are complex systems in terms of alloying elements if we look to the chemical composition. Just to give to you one real example, the so-called LEAP engine has been designed, developed, and then produced by, I don't want to make any advertisement, just sales. And then placed on the market by the Safran Aircraft Engines, international company. And this this engines, it is available to power the integration of single-axle commercial jets, Airbus A320neo, the Boeing 737-919. And why this engine is shown to you? Because this, which is an advanced turbofan, is able to put together, to incorporate very good technologies and materials, such as, for example, fourth generation of trailing technology related to the fabrication of polymeric matrix composites, and as it is bold beyond this tight use of light materials, we are used, I would say, consolidated solution of needle-based alloys. If we use lighter materials, we can expect a decrease in fuel consumption and a reduction in CO2 emissions as well as noise. Let's have a look now, if it is work, to a very short video, which is related to this LEAP engine.
The engine performance, because they transform the energy of the hot gases into power to drive the fan and the booster. On the LEAP engine, we decided to introduce a new alloy, anon aluminide. This developed for 30 years. It will be the first time that we use this alloy for a single aircraft engine. This alloy is 50% lighter than the current nickel-based alloy. So it enables us to make lighter engines while maintaining the same level of performance and reliability.
the manufacturing process of the titanium aluminum LED consists in casting followed by machining, coatings, and testings. What is really new compared to silicon parts is that the centrifugal casting is needed for titanium machined. We have already machined more than 3,000 parts. We have performed metallurgical testings. We have performed
the CFM company, which developed this blade for low stage pressure turbine for an air engine by titanium aluminide. As you heard, they fabricated the blades by casting. So taking advantage of on all the studies on cast refinement made during the years. And then they also mentioned that the blade was combined, which is another important topic not to be forget. This close our, let me say, short news, but very intensive on titanium aluminide. Now let's go on. I have lost the panel of the control of my presentation. Let me see if I can recover it. Anyway, can you hear me?
Yes, Professor.
I can go on.
Yes, Professor.
I have lost the control panel of the presentation, but it doesn't matter. I will go on again. The second class of special materials I want to mention to you are the so-called metallic glasses or amorphous metals. This is quite a little bit strange because when we talk about metallic alloys, as well as in the last case of the titanium aluminides, we talk about polycrystalline materials. And up to today, every time we discuss about metallic alloys, we have always in mind polycrystalline materials. Now we enter, and this is, I would say, still under a big development for the reasons that I will show to you, apart again some niche application also in this area. In the field, or with a concept, we are going to deal with a concept that we can have a metallic alloys which is not a polycrystalline, that is, which is not ordered materials, but which is an amorphous materials. So this is the reasons because we call it metallic glasses, because they recall to us glass-based materials which belong to the class of amorphous materials. So metallic glasses can be conceptually, even though the properties are very different, can be conceptually considered as similar to the more diffuse, the more familiar oxide glasses, such, for example, the most common glass materials that we know, that is the soda lime glass used for windows or used for battles. They are disordered structure, having a long range order. That is, in this case, when we move from standard metals to amorphous metals or metallic glasses, they are synonymous. we are going to lose the concept of grain boundaries. We have no polycrystalline materials, we have no grain boundaries. And this is a sort of frozen state of the liquid phase, which is have relevant and very important, let me say, impact on the properties of the materials itself, if we are able to fabricate it, and if we compare it with a conventional polycrystalline materials having the same chemical composition. First of all, conceptually, if we are going to start from a liquid metallic phase, and then we are going to develop the solid phase through solidification, we can remember that we have the solidification rate, which is something which can be chosen in some range. And we have also at the same time the crystallization rate, which is affected by nucleation and growth of grain size. If we want to reproduce at solid state the same disordered structure that we have in the liquid phase, we need to adopt processing technology for fabrication able to make the solidification rate sensibly higher than crystallization rate, so that crystals cannot be formed. So this means that technologies, depending on the composition, obviously on the starting materials, but the technologies which must be used in order to have a metallic glass, they must rely on very high, very high solidification of crystals inside the metals. And this cannot be achieved with all materials that we have. We have special formulations, and we have also, let me say, special techniques. But why we are interested, in this class of materials? Because, and we can resume this, as we say now, that the amorphous structure is able to give to the materials, to the metallic glass, two important properties. They can experience, like oxide glasses, a glass transition into a supercooled liquid state upon heating, and obviously upon cooling, if you are going to start from the solidification point. In this glass transition state, as well as in conventional oxide glass, we can operate control of the viscosity value on a wide range, and so this opens the possibility to have great flexibility in shaping the materials, in shaping the metallic glass. And so some examples of components fabricated, just to give you something which is not related to our sector, by a company which is called Liquid Metal, treating these kind of materials is, for example, a Gotham pattern. Second, the second very important things to remember is that if we have in front an amorphous structure, obviously talking about an amorphous atomic structure, we cannot talk about the crystalline defects that we call dislocation, which you remember, as we have already recalled, also talking about nanostructural materials. Dislocation, they are responsible, they govern many of the mechanical properties of more common alloys. If you are going to make a sort of, let me say, theoretical calculation of expected tensile strength of pure crystalline metallic materials, we can calculate values of tensile strength or strength, generally speaking, which are 1 to 2 orders of magnitude higher than the real tensile strength. And we must remember that this is related to the presence of the dislocation inside the real crystalline structures, which are a sort of weakening, let me say, objects, and thus resulting in the possibility to have ductility, to have plastic deformation, but in a decrease of mechanical resistance of the materials itself with respect to the theoretical value, which are calculated only assuming the bonding energy between constituent atoms of the materials itself. And so in this case, in the case of metallic glasses, where these locations play no roles because we have only a short range order, not a long range order, and we do not have a crystalline configuration of the bulk materials, we can expect, and this has been proved, that this class of materials, with respect to the crystalline counterparts, that means crystalline materials having the same chemical composition, they can be very much stronger, up to 3 to 4 times more. That is something which is approaching the 1 order of magnitude. And together with this, and this can open some specific sector of applications, metallic glasses are also something a little bit less stiff than corresponding crystalline alloys, and thus the combination of high strength, high expected and also measured strength, and low stiffness gives to this kind of materials a very high resiliency. That is, in this sense, an increased ability to store, to receive elastic strain energy, and then to release it. This is the, let me say, case of a supercooled liquid for the formation of metallic glass, which can be represented, generally speaking, on a very simple diagram in which, sorry for this Italian term, but this means metallic glass, just metallic glass, in which we report the specific volume of the materials with respect to the temperature variation. So if we are starting from the L phase, that is the liquid phase, in the case we are solidifying the conventional metallic alloys, we have a diminution of the specific volume of the materials itself. Remember, we are talking about metallic alloys anyways, which are very packed structures, with a, with a discontinuity, which is a discontinuity here, which is happening when we pass from the liquid phase to the solid crystalline phase. And this is due to the formation of compacted structure. In the case, we are going to form crystallines or crystals, generally speaking. But if we move, and this is something which is going also to happen for oxide glass, from the liquid phase to the solid phase without forming a long range ordered structure, that is, without any crystallization, we do not have this discontinuity in the specific volume, and we have a sort of continuous curve changing the slope, but it is a continuous curve in which the specific volume is going to be decreased without any drop like this one. And this is the reason, because we are freezing the liquid disordered let me say phase in a solid disordered phase, that is in a metallic glass. I said to you, and this is just an example, that this implies necessity to refer to special composition and to special processing technology, just to be a little bit exaggerated. But for example, this is a metallic composition, and you see how much is complicated. It's not a conventional materials, which is able to be processed in order to have a metallic solid glass. You see zirconium, titanium, niobium, copper, nickel, beryllium with specific stoichiometric coefficient. So many studies are made in this area, in this field. As well as, just to mention to you, the necessity to have a solidification rate, that is a cooling rate of materials very fast, is not conventional for conventional processing technologies based, for example, on casting. And one example, just to remember to you, because also for this we have dedicated some attention last years, is to fabricate, for example, amorphous metallic powders by using the plasma spraying technology. That is that technology which is going to be used for the fabrication of thermal barrier coatings for turbine blades and combustion chambers. Remember that plasma spray technology, which is going to deal with molten droplets, which are projected on a substrate in order to fabricate the coatings, for example, but the melt powders, they can assure cooling rates which are around 10, and this is not a mistake, 10 to 5 Kelvin or Celsius, it doesn't matter, 273 doesn't make any change, on 10 to 5 per second. So this is not a conventional technology, fabrication technology. It is one special, let me say, but just to say to you that we do have some tools, in order to assure, depending on the material's composition, the possibility that the cooling rate is higher than the crystallization rate, so that we can freeze the liquid configuration in a solid state, which becomes a disordered state, which becomes a metallic glass. Well, this is just to remember again that we are going to reduce the grain size to a 0 dimension. So is the, let me say, the subsequent step to the nano crystalline materials. And here I have a look to this, which is one of the reasons because of we are interested in this special class of materials. Here you have some comparisons, generally speaking, just to give to you an idea of how moves hardness in different, let me say, classes of steels and in the amorphous way. Hardness, strength, and fracture toughness. Well, if we see, we have a relevant increase in both of these three applications, properties, so hardness, strength, and fracture toughness. And what we, and this is the interest in this class of materials from an engineering point of view, and what is can be evidenced is a very, very significant, numerically speaking, increase in strength and, for example, in fracture toughness. This is the first consideration. Then on fracture toughness, we can say one thing in addition on the next slide. But another important concept that we must underline is that if we have in front of us a conventional polycrystalline materials, we know that we have the possibility to increase hardness and to increase strength of the materials itself. For example, by modifying the microstructure of the materials by using specific thermal treatment. And we have tools, that depends again on the materials composition, but we can have tools related to the possibility to have an increase in strength, to have an increase in hardness, because, as we said the first time we met in this course, they are both extrinsic properties of the materials itself, thus depending on materials microstructure. But every time for conventional materials, I repeat, that we move for an increase in hardness and an increase in strength, we have a decrease in the fracture toughness of the materials. And having a decrease in fracture toughness of the materials means that the materials is starting to move, let's say in this way, in a more brittle behavior. If we want to say better, we can say that the decrease in the fracture toughness stands for a decrease in the capacity of the materials itself to contrast crack propagation, which is the basic concept of the modern engineering design for structural high-performing components based on the damage tolerance approach. So for conventional materials, we can have an increase of hardness, we can have an increase in strength, and we are happy for that, but we do have always, at the same time, a decrease in fracture toughness, and we are not so happy for that. So we need to find a compromise. If we move through the class of metallic glasses, we can achieve all these three results. We can have an increase in strength, we can have an increase in hardness, but we can have, and this is very interesting from an engineering point of view, also an increase on fracture toughness of the materials, K1C. These materials becomes more resistant, generally speaking, but becomes also more resistant to damage or cracks propagation. And with respect to the fracture toughness, this value here reported 300 gigapascal per square meter, not mega like written here, but it's sorry, 300 megapascal per square meter. That's right. There is also another concept that must be underlined, because this is the fracture toughness value that we use, for example, as we have seen, when we make design based on the approach of elastic linear fracture mechanics. But we can have not the propagation of cracks, not only in static or quasi-static load application in terms of load configuration. We can have also the propagation of cracks, thus the rupture of the materials itself, when the component is subjected to impulsive loading, to impact, for example. And in this case, the parameter, always again, megapascal per square meter, which is used in order to make some design of the components, is the fracture toughness, but is not, let me say, the previous one is the so-called dynamic fracture toughness, which depends obviously on the dynamics of impact in terms of loading rate. And conventional materials, which are these curve here reported at the bottom of the picture, they do experience for a very high value of loading rate sensible, I would say also dramatic decrease of the dynamic fracture toughness. And this means that the materials is more prone to the propagation of crack. That is less sensitive, less resistance to the crack propagation. As high as is the loading rate of the impact, more brittle is the conventional materials. Well, have a look what is going to happen, qualitatively speaking, that each material has its own values. For BMG, that stands for bulk metallic glasses, we have a behavior which is exactly the opposite. I mean, these the bulk metallic glasses are able to show an increase or an increased value of the dynamic fracture toughness with the increase of the loading rate. So they become more resistant to crack propagation under dynamic conditions as higher is the loading rate. And this is not behavior which is found on conventional class of materials. Why? Because in conventional polycrystalline materials, if you are going to move towards a more brittle behavior, this means that these locations, talking about conventional materials, these locations inside the materials itself, they meet more obstacles to their movement. And in the case we are going to apply an impulsive load, that is a very high loading rate, we could stay in the situation for which this short time interval in which the load is applied is not necessary, is not sufficient for dislocation movement. And thus we have this dramatic drop in dynamic fracture toughness for the conventional polycrystalline materials. But these mechanisms, which is based on dislocation movement, which controls the mechanical strength of conventional polycrystalline materials, cannot be active in the case of bulk metallic glasses, because it makes no sense to talk about dislocation movement in an amorphous structure. And so it's a sort of revolutionary concept, and the behavior which can be defined, which can be expected, which has been observed, is not a decrease in the dynamic fracture toughness, but an increase in the dynamic fracture toughness for the bulk metallic glasses. And this is also another very interesting point from an engineering design point of view, in order to potentially be translated into structural components. We do have a different class of materials, even though we are talking about materials at the same composition of the corresponding polycrystalline. Also, for what it concerns, for example, the interaction with the working environment, that is the corrosion behavior of the materials itself. There is not a general theory about that. So each amorphous fabricated must be characterized and tested in order to understand how it is going to interact with the surrounding environment. One thing can be for sure be said in any case, that we have suppressed all the grain boundaries. And then if we have suppressed all the grain boundaries, all the corrosion phenomena that we know are going to happen in the conventional polycrystalline materials, and which are going to happen to be developed due to the existence or along the grain boundaries, cannot exist in the case of bulk metallic glasses. So that for these purposes, which are essentially related to some of the form of the electrochemical corrosion, we could say that we can expect an increase in corrosion resistance of the metallic glasses. But this is just referred to the case in which corrosion is affected by the existence of the grain boundaries. It cannot be a general statement for which instead the bulk metallic glasses materials must be subjected to specific characterization tests. Here we have at a glance also, let me say, look into amorphous aluminum alloys, that is bulk metallic glasses based on aluminum, an idea of the expected advantages. This is a chart in which we report the specific modulus on the y-axis and the specific strength on the x-axis. If you see here the symbol of aluminum, Al, is put where the arrow of my mouse is, that is here. Sorry, let's try to write, that is, okay, that is here, you see here, aluminum. So you have more or less this specific expected strength and this specific expected modulus. If we go to the area of the amorphous aluminous, that is bulk metallic glasses based on aluminum composition, we do have a very, this is a log scale, you see here, we have a very relevant increase in specific strength due to the fact that we have said before, even though more or less, well, then it depends on the formulation, the specific modulus is more or less comparable. But the increase in specific strength has been proved, is expected, and is obviously a benefit for the possibility to fabricate this special and, let me underline, very expensive components. So they cannot be found in conventional application by using the concept of metallic glasses. You have, and these slides are on your Google Drive, let me say, some potential aerospace application. And if you see, I don't want to discuss about that, I think they are explicative. We have not civil application, you see here, not civil application of this one, as well as also in this case, where aluminum beryllium based alloys has been used as a support structure for the electro-optical sensor system, but also this one is not for civil applications. Then last but not least, and since you are very clever students, also for this you would allow to me not to discuss, this is another example, to discuss in details because that's a real military application. One other aspect which characterize behavior of some bulk metallic glasses, for example, those which are based on iron or aluminum or refractory metal composition, is a specific, special, let me say, behavior in terms of breaking the materials itself. And most of times, and it depends by the interaction at atomic level, the fracture surface is able to exhibit, to show, you see here, I try to write, a self-sharpening behavior. And this has opened to some extent, let me say, the use of these materials, again, not for how to say, for standard, common, or civil applications. So very special class of materials, very, very interesting properties, with some niche application, not in the civil area, which are under development, even though for future application, even though they require very controlled and most of times not public formulations in terms of composition of the materials itself, as well as very strict control on the processing technology in order to avoid the formation of crystals inside the solid. But the interest of the common engineering for common design activities is related to the fact that they can exhibit the increase with comparison with the corresponding polycrystalline counterparts, an increase in mechanical performance in all the most important values of the mechanical resistance, as hardness, as strength, as fracture toughness, as dynamic fracture toughness, which cannot be expected at the same time for the conventional class of materials. Now, to move to some, let me say, more conventional potential applications. If you remember at the beginning, we said about, sorry, I go back, okay, you can see here, we said that we can expect something somewhat as a less stiffness value than crystalline alloys, but the combination of the high strength and this reduced value of stiffness can result in an increased value of resilience modulus, to be precise. That is the ability to store elastic strain energy and to release it. Okay, let's have a look also on this topic on a very short video which was released by the Yale University. If I am able to start. Let's have a look.
EMGs, bimetallic glass.
Sorry,
EMGs, bimetallic glasses.
The video start by saying BMG, that is bulk metallic glasses. Okay, so let's start from the beginning.
EMGs, bimetallic glasses, they are also known as amorphous metals, metallic glasses, or even they have commercial names. These are a new class of metals, and they have very extraordinary properties. They consist of a combination of elements. This might be zirconium and copper. These are metals, but typically metals are always crystalline. When you cool a metal from above the liquidus temperature, then you cool it. Typically they crystallize below the melting temperature, but if you cool them fast enough, you can avoid the crystallization. So essentially you freeze in the liquid, and the liquid just becomes slower and slower in its mobility. And at some point on our time scale, if we look at it, it just stays there. That's what we call a glass. If we make a glass out of a metal, we call it a metallic glass. And if we make a glass out of a combination of elements that let us do this very readily, we call it bulk metallic glass. This is the first step in making a cell phone case, right? So you take the elements, and then you alloy them, and then if you cool them rapidly, you create a bulk metallic glass. So then we use our sheet making method, which is a part of it is rolling, and then the sheet comes out and they look like, you know, this is one example, right? Like this is how they come out, and then you take your sheet and you can do various things. And for the cell phone, what we do is we use blow molding. So we use gas pressure to deform it. So we use this sheet, put it in a mold cavity, and then heat it again, and this is very critical. And then we deform it with gas pressure into these cavities, right? And this is how the sheet comes out then. And you do this in air, and you do this at low temperature. Right? This is something, some of the alloys you could do at home in your oven. As a consumer, you might not care that much about how it's made, but you're very interested in why would this be interesting to me. As I mentioned before, if you take this metallic glass and scratch it with most other materials, let's say you have a key in your pocket, now your key is not the hardest material, right? So if you scratch it against the metallic glass, then it will no longer scratch. So that's a big benefit, right? We buy a nice cell phone, and the first thing we do is we put this in, it's safe, right? So you would no longer have to do this. Metallic glasses are very elastic, right? So what we have done is we have shown that you can put buttons in the skin of the phone. This is one step towards like making them waterproof. And I think also as a consumer, it's attractive because it's a very green process.
Okay, just to underline a couple of concepts, in the video, it was evidenced as the deformation was obtained by using gas pressure. This because the thickness of the sheet was able to be processed with this technology. But apart from this, the speaker said one critical phase of that deformation process was the temperature. And this is a very important concept because we have something, our metallic glasses, in an amorphous state. But if we give energy enough, for example, by rising again temperature, the crystallization phenomena can start, and so we can lose the property of the amorphous state. So we must pay attention. We must pay attention because by solid state diffusion, the spontaneous tendency is to crystallize, that is, to reach the configuration for which the minimum energy is a properties or a characteristic of the materials itself. The third class of special materials I want to discuss with you, and now I think we just will be able to make the introduction, then we will continue in the lessons of next Friday, are the so-called ODS materials. ODS materials, like here it is written, which, let me move this bar, okay, which stands for oxide, oxide again, oxide dispersion strengthened materials. They are metallic alloys which are strengthened by using dispersion of oxide distance. So they are not pure metals, they are not pure metallic alloys, but they are metallo-ceramic materials. Why the interest in this class of materials? Let's just discuss about this and why they have been object of investigation. Even though the starting, let me say, idea has then been modified, and this class of materials can be used and are used in a higher number of engineering examples, as we will see at the end, but essentially in a very few cases in the aerospace. Because if you have a look here to this chart, where qualitatively we report the specific strength of the materials with respect to the working temperature, have a look here to the area of the superalloys, and have a look here to the area of the ODS materials. Well, even though they are positioned, let me say, more or less at the lower level value of the specific strength when compared with nickel-based superalloys, for which the original idea was to use the ODS materials as substituting materials, we can observe a higher allowed working temperature, up to some cases, 1300 Celsius. So what is expected by this class of materials is to have a higher resistance to high temperature and higher resistance to corrosion. Together with the possibility to have also good resistance to mechanical resistance to all those phenomena which are affected by dislocation motion, because the use in a proper way of the dispersed oxide phase inside the materials itself makes these oxide phases as low energy obstacles to dislocation movement, such that to have a potential, let me say, benefit on the mechanical strength of the materials itself, and also, for example, in reduction of creep only for those creep phenomena, which is based on dislocation movement, that is the dislocation creep governed by the power law, which was developed by Bailey Norton. But actually, to go to this beginning to the conclusion, the possibility to modify the microstructure of the conventional and known nickel-based superalloys, for example, with the gamma 1 phase, with the possibility to have the formation of tailored formation of carbides and addition of special alloy elements, still makes the superalloys as a high performing, best performing in terms of specific strength, even though we can have a maximum working temperature with something 200 degrees less than which can be allowed by ODS materials. But the standard solution now is still using nickel-based superalloys by conditioning them with the use of thermal coatings. But nevertheless, the ODS in some cases can be met, and in other applications, as I will tell to you, they are used. They are expensive materials because they need a special fabrication technology, and except oxidation, corrosion, a creep resistance based on dislocation movement, as I told to you, they have the other properties which are lower than corresponding or comparable in comparison with nickel-based superalloys. And then they have some other drawbacks, complexity of manufacturing. They cannot be repaired because they are solid solution of one, for example, metallic-based alloys with an oxide phase alloys. And so look into the application in an air engine again, for which these materials were thought to be as potential substitutes of nickel-based superalloys. All the design rely on the known solutions which foresee the use of nickel-based by working, as I told you, on coatings, on cooling, or additional cooling to allow the increase of gas temperature coming out from the combustion chamber of the engine. What can be done? So they can be developed some subcomponents and especially in the case we do have some modular concept in the design, but we need to, and we will say something later on, to refer to again, also in this case, non, let me say, conventional fabrication technology, which are belong to the class of the powder metallurgy PM fabrication technologies, in which also, and I will tell to you just for the purpose of your curiosity and your knowledge, by recurring to the new concept of the so-called additive manufacturing technologies, which will be discussed later on. Before going inside, we need to say that in order to fabricate a component by ODS materials, we not rely on casting technology. We are not going to rely on deformation processes based on the utility of the materials, but we start from powders. We start from powders which must have the composition of the desired ODS materials, and which must then be in some way treated in order to fabricate the bulk component. So the first step we must say something about is related to the powder fabrication, which is based essentially in ODS materials, which is based essentially on the concept of the mechanical milling and the concept of mechanical alloying. But we will start from here on the lessons of next Friday. I think that for today we can stop, otherwise we risk to start an argument without any conclusion. So this is all for today. If you have questions, please ask to me. Okay, now I have my panel and I can activate the video. Are there any questions on your side?
E professore, io l'unica cosa non ho capito bene quando ha trattato il discorso del, diciamo, la discontinuità nel volume specifico.
Okay. Okay. For your colleagues, the question was related. So let me share again my screen. Was related to this graph, the diagram, when we were talking about metallic glasses. This one, okay? So what does it say to us, this graph, in which we are going to start from, let me say, a metallic, generic metallic alloy, okay? From the liquid phase here, and then by decreasing the temperature, we have as a final point the solid phase of the materials. If we have a conventional solidification route, we move around on this curve, this one, okay? So we have, by decreasing temperature, a decrease in the specific volume until this critical point. Then when we have the transition from liquid to solid, that is here, we have a drop in this specific volume. That is, remembering the definition, we have an increase in the mass density. Why? Because if we are talking, as in this case, about polycrystalline materials, you have a disordered situation in the liquid phase, okay? And this disordered situation will result, when you have finished the solidification, in the short and long range order of the basic crystal structure of the materials, for example, the cubic one, for example, in which you have an atom here, you have an atom here, you have an atom here, you can have an atom here, and so on, which is a closed packet structure. And since we know that what is conserving is the mass, is not the volume, in this case, when you have a disordered situation in the liquid phase with a lot of void, with a lot of voids, these voids are to some extent, that's my mouse, to some extent eliminated when you form the crystalline structure, which has a very high value of packing factor. Instead, if you are not, must change my mouse, if you are not solidified by crystallization, but you are just freezing the liquid situation, the disordered liquid situation, you do not have this continuity, because you are not recovering, let me say, volume by forming this very compact structure, which are the crystalline base unit of the polycrystalline materials. But you are just having a transition from liquid to solid, maintaining in the solid state the disordered action of the atoms. Thus, in this case, you do not have this curve describing, even though I said you have changes also, but it's a minor effect, describing the diminution, the decrease of the volume, the specific volume of the materials by, as usually it happens, by reducing materials itself, even though at the same time here you have got the transformation from the liquid to the solid phase. It's just a matter of organization of atoms that you have in the polycrystalline phase, for which we could say also in this way, the interatomic distance is made lower because this is an ordered structure, but not existing in the liquid phase, where the interatomic distance due to the disorder is higher. And thus, when you pass from the liquid to the solid and you pass from a disorder to an order with a long range order situation, you have discontinuity of the mass density or on the specific volume as you want. It's okay? It's clear?
Perfetto, la ringrazio. Buon pomeriggio.
Buon pomeriggio. Any other question on your side? Okay, if that's the case, good afternoon. See you on next Friday. Good afternoon.